going to start talking about a new topic, rotation. So let's start by trying to decide if rotation is actually worth learning. Why should we care about rotation? Haven't we already learned pretty much all the physics we would ever need? So let's recap what we've learned to give us some context and figure out if there's a big hole that we have to fill. So here's what this talk is going to cover. We're going to recap force equals mass times acceleration and how it only applies to point masses. We're going to talk about how when we wanted to understand objects bigger than point masses, we had to learn about the center of mass. We'll show that just learning about the center of mass wasn't enough to really understand objects other than point masses. We have to learn how they spin. Finally, we're going to show you all of the cool stuff that we can explain once we do learn about rotation. We've learned about F equals ma, which was really useful for understanding the motion of point masses. Those incredibly tiny little objects that somehow still had mass, you push them with some force and you could predict their acceleration. We contorted F equals ma backwards and sideways and accumulated acceleration over time, and especially when acceleration was constant, we could use that to solve all kinds of useful problems. We cheated a bit and treated some objects as point masses when they really weren't, because unfortunately there's not a whole lot of true point masses in the world. When we got to real objects, we kind of had a problem. Real objects are made of a bazillion little molecules, and we push some of them with forces that we can measure, but the molecules all attract and repel each other via 2 bazillion more little forces. Oh, which, by the way, are all the little arrows connecting the dots in the video. And we completely gave up on ever analyzing all of those forces. So we learned about the center of mass, which was a special place in that we could treat its motion as if all of the little forces between the molecules did not exist. We learned about how the external force, Fext, is equal to mass times the acceleration of the center of mass. That was great because now we could do problems with real objects, not just point masses. Here's a big hockey puck. A hockey puck, like anything else, has a center of mass that I marked with a blue dot. The center of mass accelerates when we push the puck and moves at a constant speed when we don't. Your head has a center of mass too, and it of course moves just as nicely and predictably as the hockey puck center of mass. Isn't that enough? Who needs rotation? Unfortunately, it's not always enough to know what path an object's center of mass is taking. Sometimes we also want to know how the object's orientation keeps changing with respect to its center of mass. In other words, we want to be able to know how fast your head is spinning, which might be kind of important to you. Note, by the way, that if we had stuck with point masses, we really wouldn't care about rotation. A point mass has a radius of 0, so it can't really spin, and we can't tell if it's right side up or upside down. But when we decided to go past point masses and work with actual objects, which was a good thing, the dark side is that we're kind of forced to care about the fact that heads can spin. There are more reasons that we care about rotation. Think about a wheel spinning on its axle. Even if the axle isn't moving at all, we know intuitively that the spinning wheel has kinetic energy because it's taking a fair amount of work on my part to get it to spin fast. But all the little pieces of rubber that make up the wheel are moving in different directions, and the wheel as a whole isn't going anywhere at all, and so it won't be completely trivial to figure out how much kinetic energy the spinning wheel has. We already know that kinetic energy is a useful concept, but it doesn't seem to work so easily for our wheel, so we'd better figure out something. And we will. We have more problems too. When our bike wheel is spinning, like we said, every little piece of rubber is moving in a different direction. For every piece of rubber moving in one direction, there's a piece of rubber on the other side of the wheel moving in the opposite direction. And since momentum is a vector, they're going to cancel each other out. And so the total momentum of the spinning wheel is 0. And we know that can't be good. It took me so much pushing to get the wheel to spin, it just has to have some momentum, but it doesn't seem to. And so we'll deal with that too. But once we figure out how energy and momentum work for spinning things, rotation will be the key to understanding cool stuff like how ice skaters can spin so fast, and even how come cats always land on their feet even if they fall from upside down. So hopefully now we all believe that this rotation stuff is useful to learn, to understand cats and bicycle wheels and ice skaters, and even help to make our heads spin sometimes. Unfortunately, that doesn't make it easy, since, as we noted, energy and momentum don't seem to work quite right for spinning things. So energy and momentum are going to have to be rethought a bit, but as we said, we'll get there. Our big trick is going to be that even though all the little pieces of bicycle wheel are moving in different directions, every one of them is moving in a circle. That will make the problem easier. And there's one more really nice thing. Our 3 Newton's laws will still be enough. Yeah, the laws will be a bit hard to apply because when things spin, their parts all move in different directions, as we saw. But with a little bit of math, we can get over that minor logistical hurdle, and then we'll be able to apply Newton's laws to things that spin. And that's good, because scientists tend to be minimalists, and they don't like having new laws. And students tend to be minimalists too, because they don't like remembering new laws. So I hope we're all good for now. And that means it's time to actually learn about rotation. So let's get to it.